Hello, and welcome to our bi-weekly webinar. Today's topic, we'll be discussing LNG and AFT, two acronyms, so it's meant to be. My name is David Despars. I'm an applications engineer with Applied Flow Technology, and today we will be discussing the LNG process and how it relates to AFT products. We'll be discussing how you can model various situations within the LNG process within our core products, Fathom, Arrow, and Impulse. So as an agenda, we will start with what is LNG on a high level basics. We'll be going over an overview of the process, and then we'll be discussing how to model natural gas in Arrow, modeling LNG in Fathom, as well as mitigating water hammer in Impulse. LNG just stands for liquefied natural gas. LNG is liquid methane. What they do is LNG has a boiling point of negative 259 degrees Fahrenheit. So when it gets really, really cold, it will condense out of its gaseous form into a liquid. The density difference between the gas and the liquid is about 600 times. This will make it more economical to transport in a liquid form, such as through a tanker going across oceans or in trucks. LNG should also not be confused with NGL or LPG, natural gas liquids or liquefied petroleum gas. They're not the same thing, but the principles that are discussed within this webinar will still apply as far as how do you transport the gases, how do you transport the liquids. Here is a process map of a high-level LNG process. It starts with a natural gas well. These natural gas wells will either appear within the ocean or on shore. They're where pockets of natural gas are underneath the earth and they get drilled out and tapped into. Once they are drilled into, that natural gas will be transported to a treating and processing plant. In this treating and processing, they will separate the chemical components that are not desired, such as hydrogen sulfide, nitrogen, carbon dioxide, water. These things will be pulled out of be just a pure mixture of the hydrocarbons. After the treating and processing phase, it will go to a liquefaction process where the gas will be cooled until it condenses into a liquid. During this process, the more heavier chains, ethane, propane, things of those natures, will be drawn out of the methane gas. At the end of the liquefaction process, the methane will now be a liquid and will be shipped to some sort of storage waiting for loading. And then from loading, it will be put into ships, it will be put into trucks, however the transportation is desired. After the liquid LNG is transported to wherever it is desired, it will be shipped to receiving and regasification, where it will be boiled back into a gas so that it will be usable as a fuel. From there, it will use typically pipelines and things of that nature to be shipped to the market, where it will be used for power plants, it will be used for chemical processes that need methane, and it will be shipped to people's homes for heating and cooking, things of those nature. Here is an average natural gas composition, because a big part of LNG is the natural gas that it starts with. We've seen a large variety of mixtures within our Arrow models that are sent to us through support, and there's a large variation of mixtures found in nature. Here's just a sample one, but whichever composition you are working with will be more specific to the well that you're tapped into. So here's just a sample composition where we see mass majority is methane and ethane, as well as a few other hydrocarbons, nitrogen, carbon dioxide, and several other gases included. Mixture complexity is very important to a process design, to chemical reactions. You want to know exactly what mixture you have for your various chemical processes. However, what we found is hydraulically, there is little difference in the pressure and flow rates between a complex and a simple mixture. So what I mean by that is either using a very detailed composition like the one you saw on the previous page, or just using a simple mixture of methane and ethane. So as a thought experiment, we're going to look at this in Aero. We're going to consider a 24-inch, 25-mile pipeline that delivers 300 million SCFD, standard cubic feet per day, at 600 psia. We're going to consider two different compositions of the natural gas mixture, one being a highly accurate 10 molecules, 10 different components within the mixture, and all these will be measured within 0.01% of the mass. And then we'll also be looking at a simplified mixture containing only the molecules that make up more than 1% of the mass, in our case, methane and ethane. We're then going to compare how do these mass flows differ, what is the changes in pressures, temperatures, and various things of that nature, as well as ultimately consider the runtime. So here we have our very simple Aero model. This is just our thought experiment. The gas line that you will be working with will obviously be more complex than this, but this is just to give you a general idea of this concept. So here I have our two junctions and a pipe, single pipe. This is as simple as a model can get. You can't get any more simple. If we go to our fluid properties menu, you'll see that I'm using the two different mixtures that we're discussing, a methane-ethane mixture as well as a more complex mixture. You can make mixtures within all of our products using either NIST RefProp or ChemPack, and more of that information can be found through our help site, through our documentation. And if you have any questions about that, please reach out to us. So we have our mixture. We're going to set the boundaries as far as the flow rate that we're desiring, 300 million SCFD, the delivery pressure that we are providing it at, and then we're going to have two different scenarios, one being a complex mixture and one being the simple mixture. Here on our output tab, I've already ran both of these models to be able to see what is the difference. On the left-hand side here, you will see US customary units, pounds per second, feet per second, Fahrenheit. But then here on the right also, because we serve not just the US, but we serve international customers. And several customers will use metric as well. So I placed the metric units here on the right, so to give you a concept of the difference in scale. For the variables that we're looking at mass flow rate, velocity, Mach number, stagnation, pressure drop, temperature drop, etc. And as we're looking at these, we can see that the differences are very low. Most of them are within 0.1 difference of each other. I'm going to go back to my PowerPoint and we will look at these on a percentage basis. So comparing these two values, the mass flow rates for the complex mixture, the simple mixture, we can find the percentage difference. Percentage difference being no more than 0.5% for any of these variables that we consider to be important. Even with the density, we're using a completely different mixtures from each other, so the densities are different, but how different are they? no more than 0.5%. So all of these results are close to each other in value, but when we compare the run times with each other, they're significantly longer. With the complex mixture of that simple pipeline being 4.83 seconds, simple mixture 0.87. That is a 5.5 times increase for the complex mixture over the simple mixture. And this is ultimately a point that I'm trying to make here, is very little difference in accuracy of your results, but a much significant longer runtime. The reason for this is every time it needs to do a chemical calculation, with the mixture, it's more computationally intensive. So as far as our thought experiment goes, the simple mixture will run 5.5 times faster. The results don't differ more than 1% in this setup. I want to emphasize that it's this setup, but it's still just a thought experiment. And ultimately, the conclusion is perhaps consider using a simple mixture when you're doing your initial model building and design tweaking. Your time as an engineer is very important. You don't want to be spending 20 minutes, 45 minutes. We've seen models sent in that have 2-hour runtimes. You spend 2 hours waiting for your results, tweak a single little thing, and then you have to wait another 2 hours to get the next batch results. Consider if you had used a simple mixture from the get-go, you won't be waiting those 2 hours. You'll get results a little bit more immediate. They're close-ish to your final results. It allows you to continue to move forward. And then once you have solidified your design, you can then run the complex mixture for greater accuracy, get closer to the results that you're actually looking for, but you won't need to be tweaking as much. So you'll need to consider this for your own setups. Perhaps do a little thought experiment with your own models that you're working with. If you're working with a very complex mixture, perhaps try using a simple mixture, see what the results difference are just for the building phase. I'm not advocating that you do simple for your final draw-ups. I'm just saying a simple mixture will run faster for you. And so all of this is pertinent to the LNG process because it all starts with natural gas. Moving on to how LNG can be modeled in Fathom. After it has passed that liquefaction phase and it's now in a liquid form, Fathom, which is designed to model steady state fluid transfer in pipes, would be the tool to use. You can use it from the liquefaction to the storage phase, storage to loading, receiving to regasification, anywhere that it is liquid and in pipes. And a caveat that you're not concerned about pressure surges, you can use Fathom to model it. So we'll look at a very simple model of that. Now, once again, your system will be much more complex than this, but this is just to give you an idea of what Fathom can do for you in your LNG processes. So once you've reached your liquefaction process, you know the pressures, temperatures, however it is leaving that process, you can define those boundaries, define the pipes up to your pumps, define your pumps, give them pump curves, and then ultimately pump them into storage tanks or what have you. We also have a few modules, such as our XTS module, Extended Time Simulation, which can model the filling and emptying of tanks, if that is a pertinent thing to you. And so here is just an example of how LNG can be modeled within Fathom. When it comes to the liquid itself too, we can model liquid methane, assign it the temperature that you're running with, etc. And now let's talk about water hammer analysis. Water hammer analysis is akin to you don't want to break expensive things. Your companies have invested a good amount of money on the equipment, and Waterhammer doesn't necessarily care how much money you spent on it, it will wreck it just the same. Waterhammer occurs because fluid momentum doesn't stop on a dime. As you are moving that fluid through the pipeline, momentum is conserved, it's moving, and at the moment you shut a valve, a pump trips, something changes within your situation, that momentum is still going somewhere. And in the case of a valve shut, the fluid can't go past it, so now a pressure spike will occur and it will bounce back and forth along the pipe. Pressure waves move at the speed of sound in the fluid, bounce back and forth. And then there's also the issue that once it bounces to the other side, you will see a low pressure following it, high pressure, low pressure, and it will oscillate. And this low pressure can cause cavitation, especially when a lot of LNG systems, the liquid, while it's cooled into liquid, it is not very far off from its vapor pressure still. So low pressure changes could cause cavitation and could damage pumps, pipes that are not safe to implosion, etc. To discuss this a little further, we have a case study from Lamar University. It is the LNG Loading Emergency Shutdown Surge and Stress Assessment. You can find this case study on our website. Ultimately, what they were just looking to solve and discover was emergency shutdown procedures of LNG loading arms. What situations would create a significant pressure surge that would damage those things? They wanted to see what the forces were. And they wanted to evaluate 6 cases of operation for failure to see how would it break. And we'd recommend that too. You want to not only model the system running as you've intended, but you want contingency plans. So they used impulse to model inertial pump trips, meaning that the pump has turned off, whether it's intentional, unintentional, the pump is winding down, vent valves opening, and transfer valves closing. So any kind of valve transient occurrence will change the system that you're looking at and induce pressure waves. They also wanted to consider the valve characteristics, which would drastically impact the surge response. And what they were able to find was the pressures, where the pressures were exceeding their failure case, where it was going to break things within their system. And they were able to do a force analysis as well to reveal more concerns. Here is their model, and we'll swap over to it in Impulse in a second. But their design was working with a few tanks, pumps that were tripping with inertia. So big pumps, they don't just stop on a dime either. They will slow down. Impulse can model those changes. Pump transfer valves, main transfer valves, several valves. One of my understandings is there is a standard rule enforced by, I believe it's the Coast Guard, which says that in an emergency situation, you need to cut off the shore from the ship within 30 seconds. And so they were modeling these closing within 30 seconds. But even though you need to be prepared for that situation, you can also mitigate the damage that would occur from that situation. And so they had their loading arms ending at these control assigned pressures for the ship that they're filling, as well as a relief line during emergency situations. And they also took advantage of our scenario manager. where they were able to quickly apply these different situations, such as the system working properly, such as all pumps failing, all valves failing, maybe just one pump failed, maybe one vent failed. You can create multiple case scenarios based upon your original scenario and quickly roll out, hey, what if we changed to this type of valve? How does that change our mitigation strategy? How does that deal with our forces? And so here is a model of such. As you can see, you're able to, with an LNG system, set up your tanks, set up pressures, liquid elevations, etc. You can define your pumps, give them pump curves. You can even model 4-quadrant curves if that's of interest to you. And you can model things shutting down. You can model the valves closing at certain times, at certain rates, give them CV values, etc. And one of the things we'll point out here in the output if we run our model real quick. This being the solution progress menu, you can see that it first came up with a steady state solution and said, in steady state, how does the system start? And then it will start using method of characteristics to see how do the pressure waves propagate through the system after the events have occurred, such as your pump trips, etc. So now we have our output complete. Impulse will give you several cautions accordingly to the system that you're working with, telling you whether informational messages, such as where you're operating on a 4-quadrant curve, behavior, how you're operating from your BEP, etc. And one of the powerful things you can do within Impulse and all of our software is you can create design alerts. You have set limitations, like you have the flow cannot exceed this value, or the pressure cannot exceed a value. You know these things from your own designs, from your own systems, and what you can do is add them as design alerts. And the moment that Impulse detects that it's occurring, it will tell you that it's occurring. And so in this example, their stagnation pressure is greater than their alert. Now, is that pressure enough to break their system? They would know, you would know from your own systems. And sure, you can apply factors of safety, but ultimately it is telling you, be wary. If this event were to occur, Impulse predicts that something could happen based upon your design alerts. So it empowers you to place in your designs and your limitations, and for Impulse to respond and say, have you met them, exceeded them, etc. Another nice thing that it will do is it will highlight the values where it is being exceeded to. So now you even know which pipeline is it occurring in, time that it's occurring in, etc. From this, they were able to measure the forces as well that were propagating through their system. They were able to see the pressure spikes for the case scenarios and then try and determine more mitigation strategies around it, whether that force was enough to break things or not. You would need to determine for yourself, but it would be able to tell you a force over time. It would be able to tell you within a certain pipe, scenario basis, etc. And then what you can do further is once you have the forces, you can put them into more of a FEA or a pipe force analysis tool to determine, hey, is your pipe going to break, bend, contort in the situation that you have? So in summary, AFT software can model a variety of LNG applications. We saw this with an arrow where it will model compressible gas flow, such as going from the well to liquefaction anywhere where there's gas flowing. It can even model the regasification process to your market. So anywhere there is gas, arrow can model that for you. Fathom can be used to model your incompressible fluid flow, where it will be able to be shown in your liquefaction to storage or any other processes where you are not concerned with transients. And Impulse is designed all around modeling water hammer analysis and being able to tell you, is your system safe? Are things going to break? Etc. So modeling several situations such as shutdowns, emergencies, or just natural operations. You know, you're not going to be running your pump 100% of the time if there's no tanker to be filled up. So you need to model all your situations. And also as the cherry on top from what we covered within our error model, simpler fluid mixtures tend to have quicker solver run times than complex fluids. And while the results can be different from each other, how different are they? That would apply more to your specific application. But just as a thought experiment, try, see how your models would run with a simpler mixture while you're in the design process. You don't want to be waiting 2 hours for results. Sometimes even if it's just 10 minutes, maybe you don't want to be sitting around waiting 10 minutes for results when you could get it in 30 seconds. So something to be considered, and then you can always run your final version, your final draft with your actual mixture. So with that, I want to thank you for attending. If you have any questions, please feel free to reach out to us. You can email us at webinars@aft.com. We'll do our best to answer them. And if you have any future webinar ideas, a topic that you would be interested in hearing us discuss, and how does it relate to our products, and how can you model them, please submit those topic ideas to the same, webinars@aft.com. And we thank you. Have a good day.